Every single day, you use dozens of gadgets, your phone, your laptops, your earphones. But have you ever stopped to think about what's actually inside them, keeping everything running smoothly? Hidden inside every one of those devices is a component so small most people never even notice it exists. Today, we're diving into our case studies, ceramics and electronics, ceramic capacitors and their role in modern gadgets. Ceramic capacitors are among the most widely used electronics component in the world, and yet most people have never heard of them. In this video, we will explore what they are, where they came from, how they work, and where they're used, why something made from ceramic become absolutely essential to the gadgets that we cannot live without, and what the future holds for them.
For our listeners who may not be familiar with the ceramic capacitors, could you explain what a ceramic capacitor is and its main types and why it is considered a passive electronic component?
A ceramic capacitor is a fixed value, passive electronic component that stores and releases electrical energy using ceramic as a dielectric. It consists of alternating layers of ceramic materials and metal electrodes, with the main types being ceramic capacitors and multi-layer ceramic capacitors, and LCCs.
I've always wondered about this actually. What's the story behind ceramic capacitors?
I can explain it to you. Ceramic capacitors were developed in the 1950s when titanium was added to ceramics, increasing the dielectric constant. By 1940, barium titanium became the main material for compact, high-precision military electronics. Commercial ceramic laminate capacitors appeared around 1960s, and by the 1970s, they became essential for hybrid integrated circuits. Today, ceramic capacitors account for approximately 70% of the global market capacity.
Could you explain the key functions of ceramic capacitors in electronic circuits, particularly their roles in DC blockings, noise filtering, and resonance?
One of the functions of MLCC is decoupling, which is a shock absorber that sits next to the chip. It works by storing a bit of power and instantly releases it if voltage drops, keeping the power steady. Decoupling capacitors are primarily used to suppress voltage fluctuations or noise from power supply lines so that there is no impact to the operation of sensitive components. Next, ceramic capacitors can block direct current completely while allowing only sound waves, which are alternating current signals such as audio to pass right through. Not to mention, noises from wireless signals, Bluetooth, or spinning motors creates electrical static. Ceramic capacitors acts as a filter that catches this noise and throws it on the ground. Last but not least, due to the applicable charge and discharge super fast speeds, they are used to set timing. For example, they help the device tune into one specific frequency but ignoring all others in radios and walkie-talkies. They are found in almost all modern electronics, from smartphones and home appliances to automotive electronics, industrial equipment, and AI servers.
What are the main challenges faced in the development of these ceramic capacitors and MLCCs, and how have been these challenges overcome?
These ceramic capacitors have a low dielectric constant, leading to lower capacitance and larger size. This is improved by adding barium titanate, which increases capacitance and reduces size. Manufacturing defect-free thin layers for multi-layer ceramic capacitors, MLCC, was tough, but advancements in ceramic processing and tape casting technology enabled reliable multi-layer structures.
How are recent advancements in ceramic capacitor technology shaping the future of modern electronics?
Ceramic capacitors have been around for decades, but the innovations happening around them right now is anything but old news. Miniaturization is one of the biggest recent breakthroughs. Engineers have developed MLCCs, a multi-layered ceramic capacitors that are now smaller than a grain of sand, yet store more energy than older, bulkier versions ever could. This is a huge deal as devices continue to shrink. On the material side, researchers are engineering new ceramic components with high dielectric constants. In simple terms, that means more storage capacity in an even tinier package. With the global rollout of 5G technology, there's also been cutting-edge research into ceramic formulations that perform stably at extremely high frequencies, with lower energy loss and stronger signal reliability. In another exciting development is soft termination technology, where a flexible polymer layer is added to the capacitors and solving the long-standing problem of cracking under mechanical stress. And on the environmental front, the industry has made major strides towards lead-free ceramic materials, meeting global sustainability standards without sacrificing performances. Perhaps most excitingly, researchers are now exploring ceramic capacitors for use in electrical vehicles and AI-powered devices, where reliability, speed, and size are absolutely critical. Ceramic capacitors have quietly evolved from simple circuit components into a high-precision technology, and they're not done yet.
Why are ceramic capacitors widely used across industries, and how do they benefit the modern electronic devices?
Multi-layer ceramic capacitors are cost-effective due to mass production, which leads to consistent quality and lower cost. They are versatile, used in smartphone, automotive electronics, and file infrastructure thanks to their compact size, excellent high-frequency performance, and non-polarized nature. Additionally, MLCC package reduce parasitic inductance, improving high frequency and performance in smaller size.
Eunice, what are the main limitations of ceramic capacitors and how do they affect their reliability and performance?
Ceramic capacitors have several limitations that can affect their reliability. Their capacitance may change with temperature, reducing circuit performance, while the brittle ceramic structure can crack due to PCB bending, vibration, or thermal stress during soldering. In addition, excessive voltage can cause dielectric breakdown, damaging the capacitor and leading to failure.
Miss, I have a question. How will ceramic capacitors shape the future in modern gadgets?
Good question. The future of ceramic capacitors emphasizes miniaturization and eco-friendly production. Advances in nanomaterials enable smaller MLCCs for compact electronics and medical devices, while manufacturers use lead-free, halogen-free barrier platinate for safer, high-performance capacitors. Finally, ceramic capacitors play a vital role in miniaturizing modern electronics, enabling devices to become thinner, lighter, and more portable without compromising performance. They also support advanced technologies such as 5G communications, AI systems, data centers, and high-performance GPUs. With their small size, high reliability, and fast electrical response are essential for efficient operation.